This is the code for the 4-bit unsigned adder.
So here you can see this is input A, input B. 1 plus 0 is 1. 1 plus 1 is 2. 3 plus 1 is 4. 1. 3 plus 3 is 6.
This is the measured delay for the 4-bit adder circuit with a delay of 40 nanoseconds. This is the code for our 4-bit adder as a functional unit.
So here you can see that this switch on the far left is the control. We have input A, input B. So when the control is 0, we are sending the bus the Z state. So this and these 4 bits are the output, so nothing is being sent. I'm not really sure what these other LEDs and things are doing, but nothing is being sent to the bus. Now when the control is 1, these 4 output bits, the bus is receiving addition. So 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 3 is 4, 3 plus 3 is 6.
This is the measured delay for the 4-bit adder, but with the functional unit, and the measured delay is 80 nanoseconds. This is the code for our 7-bit shift left twice. This is the measured delay for the 7-bit shift left twice system, and the delay is 80 nanoseconds. Okay, this is the code for the 7-bit unsigned shift right 2. So we have our 7 bits as the switches, and when we switch one of the switches, the LED 2 spots to the right lights up.
That one's not part of our amount of bits.
This is the measured delay for the 7-bit unsigned shift right system, and the delay is 80 nanoseconds. Okay, this is the code for the rotate left through carry twice.
So here, as you can see, whenever I flip on the 5th bit, or the 5th bit, it rotates all the way back around to the 0 position. And then here you can see it continue to rotate.
This is the measured delay for the rotate left carry through twice system. The delay is 40 nanoseconds. This is the code for the rotate left carry through twice with a 0 flag.
So as you can see, the 0 flag's already lit up because 0 is the input. Rotates.
This is the measured delay of the rotate through carry twice system, but with the 0 flag added, and the delay is also 40 nanoseconds. This is the code for our shift left end system.
Here we have the 0 flag. Then we have our 6-bit input and our shift amount here. So whenever the shift amount is set to 0, then the input won't shift. When it's set to 1, the input will shift 1. When it's set to 2, the input will shift twice. And when it's set to 3, the input will shift 3 times.
This is the measured outputs for the shift left end system, and the delay measured for this is 80 nanoseconds. This is the code for our negative edge D flip-flop, and it's active low.
So here we have D preset clear. Whenever we want to set, we input a 1 in the clear, and these two don't matter. When we want to reset, we put a 1 in the preset. Doesn't matter there. And then we want to store D on the negative edge. You can store D. You can reset it by then by the active low, setting this to 0.
This is the measured delay for the negative edge D flip-flop system. The delay is 74 milliseconds. This is a code for our negative edge D flip-flop with 4 bits, and it is active low.
So here we have the first 4 bits of our D input, then we have the clear and the preset. So as you can see, when this goes high, it sets all the outputs to 1. You can reset that to 0. And when these are both high, you can store the value of whatever D input you want on the negative edge. And then you can reset it.
This is the measure output for the 4-bit D flip-flop system, which also has a delay of 74 milliseconds.